I'd like to talk to you about something called Bayes' theorem. And Bayes' theorem has some nice applications in probability. So we're going to start by considering this situation. Right? So a test of the HIV virus. What I mean is this is a test that tries to detect if the HIV virus is present in a subject. Detects the virus 99.9% of the time when the subject actually has the HIV virus. Sometimes that's referred to as the sensitivity of a test. Okay? What this really means is if someone walks into the office who happens to be carrying the HIV virus and they're tested, the test itself is 99.9% likely to say, yes, that person has HIV. Okay? Another way to say that is we can expect if, say, 1,000 people visited the office all having the HIV virus, about 999 of them will be told that they do have it, according to the test. Okay? All right. So, okay, let's be clear. I'm not guaranteeing that 999 out of 1,000 would be told yes. What I'm saying is that over the long run, for many, many thousands or millions of people, about 99.9% of them who have HIV are going to be told, yes, you have it. Okay? Now, we can write that in what's called like probability notation. We can say is this. Probability, P stands for probability, of a positive test result, given you have HIV, is 0.999. Okay, that's how we write that. This word in here, this little vertical bar, sometimes means such that, or given that. Okay, this is referred to, when you write something like this is referred to as the conditional probability. Okay, that's what this is referred to as, a conditional probability. Okay. So let's go back to the problem and see what else they're telling us. Okay. This next sentence here says, the probability that a subject will test positive when they do not have HIV is 0.7%. Okay? That's sometimes referred to as the false positive percentage or proportion. In other words, there are going to be some people who are going to go and get tested for HIV. They really do not have it. They're not carrying the virus. But the test is going to still tell them yes. Yes, they are. Okay, that's an example of another conditional probability. We can write that this way. The probability that someone has a positive result, given they don't have HIV, is 0.007. Notice I'm choosing to write these as decimals. That's fine. Okay? So that's another example of another conditional probability. Okay. All right? And then lastly, we're just given a fact. Suppose that 1% of a large population is HIV. That actually turns out to be a pretty high number, actually. It's not 1%. I think for the United States, it's less than that. It's probably about a third of that. Okay? So let's think about what we might be interested in here. Because most people don't walk around knowing that the virus is in them or not in them. They go and take a test. And then the test gives them a result, right? And it is as positive or negative, and they assume that the test is correct. So what we're really interested in here is the following. We're interested in answering this question. What is the probability that a person who has HIV, given they got a positive test result? When you think about that, that's different than the information that's given in the problem. We can write that in our conditional probability notation. So let's make a note here. Okay. We want the probability that someone has HIV given they got a positive test result. Okay? And one of the most common misunderstandings is that this probability here, this probability that I'm saying we're interested in, is the same as that probability. Okay? Just to reiterate, this top probability is saying the person we know is a carrier of the virus, how likely is the result to come back positive? This is saying someone came in, they got a positive result. How likely is it that they actually have the virus? Okay, so let's get started on how we're going to work this out. What we're going to do is we're going to make a sheet diagram to help us consider all the different cases. Okay, so first thing we're going to do is break the population into two groups. There's people who are carriers of the virus and people who do not have the virus. Okay, and if we remember that last sentence on the problem, we were assuming 1% of people were carrying it. Again, that's a pretty high assumption, but we'll just live with it for now. Let's pretend. So we could say the following. We could say that probability of being along this part of the population, or this branch, is 0.01. And what does that tell us about this other branch? Well, there you go. There's the other 99% who are not carriers of the virus. Okay, so that's how we start. Now, here we go. Consider this. Someone who's an HIV carrier can go and get a test. And when they go and get that test, then one of two things can happen. They could get a positive test result, which is presumably what you'd like to have happen. Okay. Well, we actually know what this probability is, because we learned earlier the probability of a positive test result given they have HIV was 0.999. It's called the sensitivity of the test. The test was 99.9% likely to detect the virus in this group of people who we know have it. Okay. Let's talk about this group. Pause for a minute and think about what that might mean. So we can say probability that goes there is 0.001. The question I want to think about is, what are these people experiencing? What do we know about them? So this group of people are the people that are actually carrying the virus, but now, because of the test, they think they're not carrying the virus. So this is the probability of a negative result given, or such that you really have the virus. So this is sort of a group that is relieved, but they shouldn't be. Okay, let's go down to the people who don't have HIV. Okay, people who don't have HIV. Well, what can happen to them? They can go in and they could still get a positive test result, even though they're not carrying the virus. Hopefully they'll go in and they'll be in this category. Here are the people that don't have HIV and are getting back a negative result. Okay, we know the probability that goes on this upper branch. We wrote it down earlier. Probability of getting a positive test result, even though I don't have HIV, is 0.007. We can put that here, 0.007. And that means that this probability down here is 0.993. So I'll write this the following way. Probability, positive test result given no HIV. And this is the probability of a negative test result given no HIV. Okay. So, the question is, how can we use this tree diagram to find the following probability? The probability that I really am carrying the virus if I tested positive. That's what I want to know. To answer this question, what we need to first do is figure out where are all the people that are being told that they are positive, that they have the virus. If we think carefully, there's actually two locations. It's this group of people up here. They're being told that they have HIV, and so is this group. Okay? So what we need to do is figure out what's the total probability of being in one of those groups. The total probability of being in one of those groups, meaning I'm in this group here, or I'm in this group here. Okay? And you can't be in both groups, so what we know is we can just add the probability of being in the first group to the probability of being in the second group. Okay? Because there's no way you can be in this group and that group at the same time. Okay, so let's write down the probability of a positive test result. Well, what's the way this can happen? I could have HIV and then be given a positive test result, given I have HIV, or, which we know we're going to add this, a person could not have HIV and then still be told they have a positive test result given that they don't have HIV. These are the two ways that a person can receive a positive test result. we can fill in all these numbers. So the probability, this part here, 0.01 times 0.999 plus 0.99, the 99% who are not carrying the virus, times the 0.007% of that 0.99 that are going to be told that they are carrying it. We just need to multiply those numbers and add. So we multiply all this together, we get this number, 0.01692. Okay? So it's fun to just think about for a second what that number means. You should do this during the problem. This is the percent of the population that are being told that they are positive, have a positive test result. Okay? And if you think about this group, not all of them are, right? There were two parts here. Here's the people who actually had it and were told yes. Here's the people who didn't have it and were told yes. Okay then, so what do we do with that number? Well, remember, our goal is to find that probability. So the probability, okay? And to do that, what we know now is that the denominator of that probability is 0.01692. And the reason for that is that's all the people who are being told that they're positive. That's the sample size, so to speak. Okay? On top, what we want is the probability that someone had HIV and a positive test result. Because that's what we're saying. Saying, what's the probability you actually have it, given you had a positive test result? Okay? That number can be found this way. 0.01 times 0.999 over 0.01692. So after we divide this, we get about 0.59, or 59%. So if you think about that number for a minute, it's a little bit surprising. What is that telling us? We really think about what that's telling us. What this result is telling us that if we do receive a positive result, there's only a 59% chance that we actually are carrying the virus. So you could look at this a couple of ways, right? One thing you could say is, okay, well, maybe that's sort of a good thing because if I get a positive test result, I don't have to panic right away. There's a pretty good chance I don't have it. Okay? The other way you could look at it is you could say, well, a lot of people are being told they have it unnecessarily. You're scaring a lot of people, right? So what that means is typically when you have these kinds of tests for any kind of virus or condition that you're looking for, this number, your false positive rate, you kind of have to worry about. You don't want that to be too big because that means you're making a lot of people worry unnecessarily. Or in some cases, you might even start to treat them as if they were sick when in fact they're not, and subject them to lots of drugs and spend a lot of money treating someone who actually doesn't need those treatments. So there's some bad side effects to having that number be high. The other thing, too, is that could fix this a little bit is make sure this sensitivity, 99.9%, was a little closer to 100. But that's pretty close to 100 in this case. It would be nice if it was a little closer. But it's really this number, this false positive rate being almost 1%, that's creating this issue. So a fair question might be, how come this false positive rate of 0.7% is making our number come back in such a way that we have so many people being told they have it when they don't? You have to remember you're doing 0.7% of 0.99 of the population. So 0.99 is a big number, and you're multiplying it by 0.7, which seems small, right? But as a result, if you take, it ends up making that product fairly large compared to the product in the numerator. And that's sort of one of the other reasons why you end up with the surprising result.